1.1 is on page 2, talks about systems of linear equations. And given a system of linear equations in two variables, that means those are a bunch of straight lines in two dimensions. A system of linear equations in two variables will fall into one of the following three cases. Either the two lines would have one solution. That's called consistent because it does have a solution. Or the two lines, if you glance at them, you'll notice they're parallel. That means no solution. You could use the empty set notation if you want. This is inconsistent. Or the third case, the lines are identical. In this case, this is consistent and we have an infinite amount of solutions. So, we really need in this class to make sure we get the difference between those. I'm going to start with a system of equations, and we're not graphing for sure. This is on page 10. By using elementary row operations or on equations or on the augmented matrix, follow the systematic elimination process described in this section. Let's talk about what that is. We're going to start the process doing one thing and one thing specifically. The goal is to make this a 0 first in that specific order, then to make that a 0 after. So the way it works, we start off by making this a 0, and we do that by, if we multiply the top, now I could divide the top row by a 2, the book will do that for sure. I'll do that at the end. If I multiply the top row by 5, multiply the bottom row by -2 and add the 2, then that would be a 0, and that's the goal. Now, the author would like to make that a 1 every single time. You could get around that. But just to follow on this first assignment, if I want to make this a 1, that means I'm going to divide this row by 1. And to really keep up and tell me what you're doing, you're going to take row 1, we're going to divide it by 2 and put the result in row 1. So we're going to have x sub 1 plus 2x sub 2 equal -4. Again, I don't mind you doing this at the end, but in the first couple of problems, I'm just going to fire off with what the author wants and get this out of the way. Now, my goal is to make this a 0. That's the first order. So, if you multiply the top by a -5, if your top is row 1, multiply it by -5, add it to row 2, put the result in row 2. So, if I take row 1, I'm using it, but I'm not changing it. So, if I multiply this by a 5, that would be a -5. That's -5x1, -10x2, and 20. And if I add those, I'll get -5 plus 5, which is 0, which is what we want. -10x2 plus 7x2 will be -3x2. And if I take 20 plus 11 is 31. Now, the goal is to make this a 0. When I divided row 1 by 2, that should have been a -2. And when I multiply that by 5, that should be, by -5, that should be a 10. And 10 plus 11 is 12. So again, normally I would really zero things out and proceed, but this author likes to take those in steps. They will make that a 1. So we'll take row 2 divided by -3 and put the result in row 2. So row 1 we leave alone. So system of equations will always look like this, a pair. 0, negative, a positive x2 and a negative 7, and x1 plus 2x2 equal a negative 4. If I'm not, negative 2, right, we changed that, right? That should be a negative 2. There we go. Now, to make that a 0, I would take row 2 multiplied by negative 2 and add it to row 1, put the result in row 1. Row 2 is 0, x2 equal negative 7. If I multiply this by a negative 2, that's a 0, minus 2x2 equal 14. If I add those, that's x1. If I add those, that's 0. And if I add those, that's a 12. And once I get this far, I could tell that x sub 1 is actually a 12, and x sub 2 is actually a negative 7. And that would be the solution. Another way of doing this is for me to use augmented matrix. Instead of grabbing all of these things with me, there is a set organized way of doing this right. And it really saves a lot of work. That is, if I take the coefficients, make sure they're lined up, x1, x1, 1 and 3 for x1, negative 5, negative 7 for x2, 1 and 5 for x5. They used to put a line, now they're no longer putting that line. This is called an augmented matrix. And we proceed the same way. We say, alright, the first goal is to make that a 0. How do you do that? Well, multiply this by a negative 3. So take negative 3 row 1 plus row 2 in row 2. And what do we get? So this is 1, negative 5, and a 1. If I multiply this by a negative 3, wouldn't that be a negative 3, a 15, and a negative 3? And if I add those, wouldn't I get a 0, an 8, and a 2? Right? And now, the author will make that a 1. I'm going to make an exception. I'm going to do that at the end. I'm going to make this a 0. How do you do that? I'm going to multiply the bottom row by 5. So I'm going to take row 2 multiplied by 5. I'm going to take row 1 and multiply it by 8 and add those. Put the result in row 1. That will do the trick. So this turns out to be more constructive. It works much better and really efficient. This row, using not changing, if I multiply the bottom row by 5, that's 0, 40, and 10. The top row by 8, that's 1, negative 40, and 8. And if I add those, I'll get 1, 0, and 18. And this last stage, I could say easily, you know what? Let's take row 2 divided by 8, put the result in row 2, and I'll be getting 1, 0, and 18, 0, 1, and 1/4. And hence, I could figure out that the solution to this problem, x sub 1 is 18, and x sub 2 is 1/4. And you could always check and see if this works. Okay, I do see a typo right there. If you multiply row 1 by 8, that would be an 8. And when you add those, you get that to be an 8. Normally, that's not something that we do. And I'll show you how that works once we get more into it. For now, this is just... And I should have added here that we should also take row 1 divided by 8, put it in row 1. Now you could do that, but normally we don't do that. If I divide by 8, that would be a 1, 0, and 8 divided by 2, 9/4. So the solution to this system would be 9/4 for x x1 and 1/4 for x2. Now, a matrix is in triangular form if this triangle happened to be 0 or this triangle happened to be 0. What's so special about a triangular form, you could read what this variable equal, plug it in there and solve for this variable, plug it in there and solve for this variable. Remember, those stand for like x, y, z, or x1, x2, x3, and so on and so forth. So in the majority of this book, problems are already solved. You need to make the connection. You might have to do a bit of work. It is important that you understand the concept way more than just the solution. The solutions are going to be given most of the time. So it says consider each problem 5 and 6 as an augmented matrix. Now I prefer to put the line, they don't. I'm going to add the line to it. State in words the next two elementary row operations that should be performed in the process of solving the system. To solve the system, I need to make that a 0. And to do that, I would take -3 times row, this is row 1, this is row 2, this is row 3. Add it to row 4, put the result in row 4. So that's how you're going to show me your work. The chances of making a mistake is high. So to ensure that I see what you're doing, you should really write those out, and that's not by choice. And if I multiply this row by a 2, by a -3, that becomes 0 plus 0, well, 0, 0, 1, 2, -3. If I multiply this, that will be 0, 0, -3, -6, and a 9. And if I add those, I will get a 0, 0, 0, a -5, and a 15. And here we have just made this triangular, and that's perfect. Meaning I could solve now. I could pretty much, they just want to say, okay, how would you do that? That's really how you would do it. Now, there is state towards of the two elementary operations. Okay. Now, if I am to take row 5 divided by -5, put that back in row 5, and I could take row 2 divided by 2, put the result in row 2. And what does that do? That will give me a 1, 0, 0, 0, -6, 4, 0, -1. If I divide this by 2, that's 1, -7 halves, 0, and a 2. Again, I'm going to put that line. 0, 0, a 1, 0, a 2, -3. And if I divide by a -5, wouldn't that be 1 and -3? And that's normally what you would do. On 8 of 10, it says the augmented matrix of the linear system has been reduced by row operations to the form shown below. In each case, continue the appropriate row operations and describe the solution set of the system. Well, what do we have? If this is an augmented matrix, right, I could look at this and say, all right, let's see. The only thing I could do pretty much is divide this by 2, right? That wouldn't change anything, but here it is. Row 3 divided by 2, put the result in row 3. That would mean I have 1, -4, a 9, and a 0. 0, 1, 7, and a 0, 0, 0, 1, and a 0. This says x3 is 0. And if I put that there, doesn't that mean that x2 plus 0 is 0? And if both of those are 0, that means x1 is 0. So that's one unique solution. And if I really would do what they want in this book they want all of these to be 0. And I just want to show that, again, we don't do that most of the time. Half of the problems done, you just have to do a bit more. So we start off first by making those zeros. It's already 0, that's a 0, it's already there. If I take, first step, row 3 divided by 2, put the result in row 3. That would mean I'm looking at 1, negative 4, 9, 0, 0, 1, 7, 0, 0, 0, 2, 0. Next step. If I make that a 0 and that a 0, oh, look at that. I love it when I say something and I just copy it down. So, to make this a 0, I'm going to take negative 7, row 3, plus row 2, put the result in row 2. Leave some space. If I multiply this row by negative 7, that's simply 0, 0, negative 7, and 0. So 0 plus 0 is 0. If I add those, that's a 1. Negative 7 plus 7 is a 0, and 0 plus 0 is 0. And to make that a 0, I'm going to take negative 9 row 3 plus row 1 in row 1. So if I multiply this bottom row by a negative 9, that's going to become a 0, 0, negative 9, 0. If I add those, I'll get 1, negative 4, 0, and 0. And the last stage, I want to make that a 0. I must use the middle row. So if I take 4 row 2 plus row 1, put the result in row 1. So I'm showing you this because that's normally what we go for. And I'm just trying to show you how much work that is. Most of the time they're going to do the work for us. If you multiply this row by 4, this is the only piece that's a 4. When you add those, that's a 1, that's a 0, that's a 0, that's a 0. And here they say, well, look, x1 is a 0, x2 is a 0, and x3 is a 0. So this is normally what they want. If I'm just solving for the sake of solving right there, actually I would have went from here. I would have said 2x3 equals 0, x3 equals 0, plug it in and plug it in, and that's that. But we are after the triangular, we are after, this is called reduced raw echelon form.